Imagine that we are given a system of differential equations, like that, with unknowns y1 through yn. These are unknown functions. And there is the independent variable t, which I am most likely going to call time, because it's shorter than calling it an independent variable. Although we are aware of the fact that it need not be time. It could be location, whatever, some parameter. And the specific form that we are interested in is the one that we saw previously. For every unknown function, we have a formula for the derivative. Now, in the previous lecture, we learned that we can actually analyze the behavior using slope field, looking at orbits, looking at stability, things like that. That was very nice. But today we will have a different question. Imagine that there is a specific solution that we are interested in. Because it's a specific solution, it most likely came in the form of some conditions, typically initial conditions. So there's specific time t0, and at this time I know all the unknown functions, I know how they start, and I want to know how this particular solution, because these functions together create one vector solution, I want to know how this solution proceeds. Unfortunately, my system is unsolvable analytically, so what do? I have to develop some numerical methods. Let's have a look at the setup, which is actually nothing new. We saw this already before when we were doing Runge-Kutta methods for one equation. So what's the setup? First of all, I ask myself, on what interval do I want to see my solutions? That's a good question. It's natural to start at time t0, so that would be the starting point for our interval. And then for the other end, I will use the notation that tells me the length of the interval. So the endpoint will be t0 plus capital T. Now we take this interval, we split it into equal parts. So we have partition size. And typically I was calling it n, but unfortunately here n is the dimension of the system. So I have to choose another letter, let's say m. I have my partition size. When I have partition size, this interval of length capital T splits into m pieces, and one of them has length, here it comes, step size h, which is t over m naturally. And once we have the step size, once we have the partition size, we get a partition which is a set of specific times t0, t1, and so on, tm. So let's try a picture. Here is the time axis, here is t0, and let's say here t0 plus capital T. And we split it into several intervals, let's say into 3. So this will be t1, t2, and this guy will be simply t3. My solutions are floating around their graphs over here, and my aim is to find approximations at exactly these times, these specific times. So every function, y1, y2, and so on, will be replaced by a specific number of points, which is given by the partition size plus 1. There is one more extra point. So how do I write it? Well, let's say this way. Solution yj gets replaced or approximated by points yj not yj1 through yjm, and j is between 1 and n. It's a little bit unpleasant that I have to juggle two indices, but that's because I have more functions and now I have more time points. So this is my task, to find approximations y0 through ym. How do I get them? Well, the first approximation at time 0 is essentially given, or actually given, in my initial conditions. Let's put it over here. So let's say that this is the initial value for function y1, and this is the initial value for function y2. So this is y1, 0, I can see it here, and this is y2, 0, and let's not put more functions into the picture. It's confusing enough as it is. So where do I get the next approximation? Well, we talked about Runge-Kutta methods, and the easiest of them was the Euler method, and it was actually the basic idea on which all the other higher order methods were based. So let's focus on the Euler method. we were moving using tangent lines, using specific slopes. So I'm sitting here at time t0, and I want to move from this point with my solution y1. I need to know the derivative. Where do I get it? The answer is from the differential equation. I need to know time, which is t0, I know it. And I need to know the values, the local values, the current values of my unknown functions. But I do, because I know y1, I know y2. So I get my slope, and I use it to move by a tangent line. And this is the step size h here, okay? The familiar formula. I can do the same for the function y2 because I have a formula for the slope here. So I move with my function y2, let's say this way. And if I had more functions, I would move them as well. You know what? I think I have room enough for y3 over here. So why don't I do it? I move to time t1. Notice that it didn't make sense to try moving y1 farther on, because I would need the derivatives at these more advanced times, and for that I would need to know the functions y2, y3, and so on at these advanced times, and if I don't have this information, I cannot move on. I have to go like that in parallel for all functions at the same stage. Now I know y1, y2, y3 at time t1. I can substitute it with t1 into my right-hand sides, and I get the slopes at time t1. So I get this slope, and this slope. I use it to make another step with size h. Here I go. And then again, I know all three functions at time t2, so this can be substituted into the right-hand side. I find the slopes, and I use them to move on. So this seems to work really nicely. I just have to be organized a little bit. Notice, if I wanted to use the midpoint method, then I would move just half the way through. I would substitute these locations into the right-hand sides, and I would get the slopes. And then I would get those middlish slopes to move on by the whole step. So the midpoint method also works like that. The Hoyne method, once I get here, I could get approximations of the slopes here at the end, and then use the average of slope here, and move by that average. I mean, everything can be done also with systems. So I could use RK4, and I could even use RK45, this adjustive step size, and things like that. Everything that we learned about just one differential equation, solving it numerically, can be also done for systems when I go in parallel. Let me just capture it in a formula. So we are sitting at some time ti, for instance, ti, and we want to move to the next location with our function. So the approximating formula goes like that. The next value for a specific function, yj, will be called yj I plus 1. So I'm moving time by 1. How do I get there? Well, I have to look at my current location, which is yj I. Then I have to take the slope at that particular location, which is capital F, ti, that's the local time, and now local values of my unknown functions. So that's y1 I, y2 I, and so on. I keep substituting until I get to the last function, but I have to use the local approximation, yn I. That's the slope, and this I multiply by the step size. And that's the universal formula for my Euler method when applied to systems instead of just one equation. That was easy, wasn't it? Let's give it a spin. So I will erase, well, now that I'm thinking about it, let's erase it all and let's play. Here we have a 2x2 system that we encountered before in the previous lecture, and so we know that it's unsolvable analytically, which makes it into a very proper example. We are curious about the solutions because we saw the slope field and it was really, really interesting. So I will look for the solution given by these initial conditions. The values are 1/2 and 1. And I will be interested in how it looks like on the interval 0, 4. Here we go. So that's the range for time. I choose a partition size, well, something nice. Let's say m is equal to 4. That's a very nice partition size, because then the step size is 1. And once we have the partition size or the step size, we can see that in fact we are interested in times 0, 1, 2, 3, and 4. So far so good. What's happening at time 0, which is t0? Well, there we know the values. So x0 is simply 1/2, which is 0.5, and y0 is 1. And we are done. That was nice. Okay, so we know what's happening at time t0, and now we move to time t1, which is 1. Well, we know the location where we are sitting. Right now we are sitting at location given by time 0. We have the values, so we can substitute them into our formulas, and we get the slopes. The slope for the x variable is, okay, I take 1 for y, and I get 0. So far so good. The slope for the y variable is y minus x, which is 1 minus 1/2. This is 1/2. So let's approximate our functions. At time 1, the function x has value x1, or the approximation x1, which is the value at 0 plus the slope times the step size. That's the formula. And obviously, the same formula will be working for the function y. So, how much is it? That's a good question. Well, let's see. The slope for x is 0, so this is 0, and we just get x0, which is 1/2. And for y1, we get y0, which is 1, plus 1/2 times 1. Okay, let me write it down. This is 1 plus 1/2 times 1, which is 3/2. So, to conclude, x1 is 1/2, y1 is 3/2. Let's try some pictures. How much room will I need? 2, 3, 4. Okay, let's try it here. This is 4, this is 2, this is 1, this is 3, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, time x, y. So these will be graphs of my unknown functions. Typically, I would actually visualize them in one picture, but let's show that these are actually two independent functions. At time 0, the values are 1/2 and 1. So for x, here is 1, the value is 1/2, and for y, the value is 1. So this is x0, this is y0. And then when I move to time 1, the values are 1/2 and 3/2. 1/2, so this is x1, and 3/2 is somewhere over here. This is y1. So we see the graphs of the functions, and actually it's a good idea that I have them separately, because otherwise the picture would be too crowded over here. Okay, that's one thing that we know how to do. Another thing, well, I'm not sure I know how to do it, but let's think about it. What is the graph of this solution as a vector function? At time 0, here is the x-axis, here is the y-axis. The x-axis is pointing towards you. Okay, it goes like that, perpendicular to the blackboard, but I cannot draw in 3D. Now, the coordinates of this point, if I see it as a point in time, as a parametric curve, is 0.51. So let me choose 1 somewhere here, and then it goes, let's say, here. 0.5 and 1, it's over here. This is the point x0, y0. And then we move to time 1, which is here, and I sort of imagine virtual y-axis and virtual x-axis, And now I'm looking at a point 1/2 3/2. 1/2 and 3/2 is somewhere around here. But we have to imagine that this is happening in 3D. So it's here, and I'm going up like that. Interesting. Well, I think I will ask Maple later on to do a visualization. I'm not sure it's worth following this path. What I can do easily, relatively easily, is to show the orbit, which is essentially a recording of the trajectory. So the point is 0.51. Here is 1, here is 1. This is the x-axis, this is the y-axis, 0.51. This is the starting point, x naught, y naught. And the next one is 1/2 and 3/2, which is over here. So this is, well, x1, y1. And I see location at time 0, location at time 1. We are going this way, by the way. Okay, let's move on. Now we know where we are, and we can use this information to find about the slope of our unknown functions at that location. So for the function x, we have the slope given by y² minus 1, which is 3/2 squared. This looks like 5/4 to me, after I subtract 1. And for the function y, ky is y minus x, which happens to be 1. So that's information at time 1, and using these slopes I can move forward and get information about time 2. Let's see, x2 is x1 plus the slope times the step size. x1 is 1/2 plus 5/4 multiplied by 1, which happens to be, 7/4. Looks about right. y2 is y1 plus the slope for y multiplied by its step size, which is 3/2 plus the slope is 1 times 1, and this is 5/2. Interesting. Okay, let me sum it up. x2 is 7/4, y2 is 5/2. So far, so good. Okay, let's move here. 7/4 is for x. 7/4, it's 1 3/4. 1, 2, 1 3/4 is here. So this is x2. And y is 5/2, which is 2.5. 1, 2.5 over here. This is y2. Okay, 7/4, this is 3/4. Time 2 is here. Auxiliary axis, 7/4 looks here. I go up to 3/2, somewhere here. Well, okay. I will wait for Maple for the visualization of the graph, 3D graph. Let's move here, orbit. This is much more hopeful. 7/4 is somewhere around here, and 2.5 is somewhere here. This is the point x2, y2, and we move there. So time 0, time 1, time 2. It seems that the bug was actually crawling faster now. Interesting. Okay. Here we have information about time 2, and let's ask what we learn about the slope. Well, kx is y² minus 1. 25/4 minus 1 is 21/4. Do I really want to keep going? Ky is y minus x, 3/4. Well, I think I will ask Maple about it. So let's ask Maple about it. But you see how it goes. I just keep going, moving to the right with time, and getting approximations of my functions. And I can visualize it in many ways. Actually, the orbit looks like a nice visualization, also the individual graphs. Quite telling. So, here we go. I load my system and my initial conditions. Hopefully it's the right one. Y squared minus 1, y minus x, that's the system. Initial conditions, everything works. I'm not calling any special procedure. I simply programmed it by hand. And when you look at the formulas, you will see what's happening here. This is the slope for x, which is y squared minus 1. And this is the slope for y, which is y minus x. And then I use the slope multiplied by the step size and add it to the previous location, and I get new location. So essentially this is just a code, and then there is a long code with visualizations. There is many of them. So first of all, this is the individual graphs. The red curve, the darker one, that's for x, and it seems to be working reasonably well. And for y, it's the orange one. And yeah, I guess it's about right. The scale is different, as you can see. The red curve x goes up really sharply, and therefore Maple actually scaled the y-axis. It shrinked the picture in this way. So that's why it looks flatter, but otherwise okay. Let's have a look at the orbit. For the orbit, we get small step, larger step. Yeah, this seems to fit with my picture. And then, well, perhaps it was a good idea to stop calculating it by hand, because you can see x got really large and even larger. So yeah, I think I did the right thing. By the way, this green dot, that's the location 1, 1. That was the stationary solution or stationary orbit now. And we figured out, and we confirmed it by linearization, that there was an unstable focus. So this is just out of curiosity. Anyway, let's compare it with the actual solution, which actually Maple determines also numerically. So we will be comparing one numerical solution to another. Well, I talked about it. This equation cannot be solved analytically. But numerical solution of high quality by Maple compared to this work by hand, essentially. Here we go. Okay, 3 graphs here. In the first graph, we can see the actual numerical solution, I mean the high quality, in blue, and our approximations in red. Dark red, that's x function, and it's accompanied by a slightly darker blue, which is turning up as well. Well, the general trend is there, but otherwise it's not all that great. The light red, sort of orangey, is accompanied by a lighter blue, which is turning downwards. Again, the general trend is there, but it's not anything special. Here is the promised 3D picture. Time axis goes to the right, y-axis up, and the x-axis is going against us. And as you can see, the 3D graph, again, it's not anything really special, and we can expect that because the step size 1 is atrociously large. So nothing nice there. Okay, here is the orbit. Our orbit is supposed to go around, but instead it goes, well, you can see how it goes. It goes all the way to the right. Okay, let's try a smaller step size. How about if instead of 1, I put 0.1, which I definitely don't want to do by hand. And let's go up again. First individual graphs, x and y. And now the match is better, definitely better. It's still not great, but let's remember, this is Euler method, which means it's a method of order 1. It's a weak method, but still, I think it's a fairly respectable result. Here is the 2D situation, our graph. Time goes to the right. Yeah, did I rotate it properly? More or less. Okay, so I shouldn't lose myself in this turning business. Yeah, it's not too bad. And here, the orbit. Yeah, it's also quite respectable. But of course, it's not really all that great. So we move to, let's say, 0.01. That's a more realistic step size. And now, well, the orbit, it's almost a perfect match. This is really good. But of course, we do not see the locations, we do not see velocities. We talked about it in the previous lecture. Here is a 3D graph, which is fairly good. And finally, here, the individual graphs, again, a pretty good match. Just out of curiosity, what happens if I still decrease the step size 10 times? Then the code would run 10 times longer, and I think we can afford it. Yeah, well, That's almost a perfect match, I would say. This is really nice. Do I see any blue anywhere? Yeah, occasionally I could see a little bit of blue along the edges. So there are two curves. We just don't see them. Yeah, this is a perfect match. So what we just saw is that the Euler method is really quite good, actually. And if we used higher order method, then it would be even better. And we can use them. Essentially, this whole lecture could be summed up in just one sentence. Everything that we learned about Runge-Kutta methods for one differential equation of order 1 is still valid for the systems. We just have to adjust to the situation when we are calculating several functions at the same time in parallel. That's the only difference, otherwise everything is wonderful. And that's essentially it for this rather short lecture, because the main message is fairly simple. But before we leave, just one more remark. I talked about systems being, let's say, from a certain point of view, more useful than linear differential equations of higher order. And this is one of the reasons. In this way, we can solve systems really nicely. It's a fairly simple and reliable numerical procedure. But for a single equation of higher order, we do not have really anything comparable. And that's why people, when they're solving numerically, prefer to change equations into systems. And let me show you something. Here I have a nice equation. It's a differential equation of order 2, and it's even linear. So we can solve it easily by hand using lambdas and, let's say, the guessing method for the right-hand side. It's non-homogeneous. We can see number 1 on the right. Some initial conditions. Of course, Maple can solve it too analytically, no problem there. And Maple claims that the solution is 1 plus e to negative x times x. Now that I look at it, I can see that lambda is negative 1 of multiplicity 2. That's why this exponential is multiplied by x. That's the trick with double characteristic number. We have a graph, not really interesting, quite frankly. Now it gets interesting. I will ask Maple to solve it numerically, but I don't specify how. I simply say, please solve it numerically. And the picture looks the same, which this is not all that important, but it's a not confirmation, it's an indication that perhaps things are not totally wrong. When I look at the code, I can see RKF45. So Maple used Runge-Kutta Fölberg method, RK4 for calculating and RK5 for checking the error, which is fairly reliable. But what I can do, I can ask Maple to give me more details about how this numerical calculation was done. So let me run it again. And now I look at it, and I can read on the second blue line that Maple converted my equation to first-order system, and I can read the system in the square brackets here. So even without me telling Maple anything about how to approach it, Maple automatically converted my high-order differential equation into a system and solved it using Runge-Kutta methods. So this is really something that is used in applications. It's a viable method. And that's happy end of today's lecture. In the next lecture, we will look at some applications. Hopefully you will enjoy it. So see you there.